There is a strange contradiction woven into the way we understand the past, a quiet paradox hidden in plain sight. We are a species obsessed with recording things, measuring things, naming things. We can tell you the exact second a satellite left its launch pad, the chemical makeup of distant stars, the speed at which galaxies drift apart. We can map the seafloor, image the surface of Mars, and watch the weather change in real time on the other side of the planet. And yet, for all that certainty, for all that precision, the history of our own world is filled with gaps so large they swallow entire eras. You might imagine that the closer something is to us in time, the clearer it becomes, but the truth is the opposite. The deep past, the ancient past, the pre-human past, holds more shadows than light. It is a book missing most of its pages, left open on a table long after the ink has faded. You may have never thought about it this way, but here is the paradox. We know more about some creatures that lived tens of millions of years ago than we do about our own ancestors from just 100,000 years ago. A tyrannosaur that died in a swamp during the Cretaceous can leave behind a nearly complete skeleton, but a human who lived in Eurasia during the last ice age may leave nothing at all. The further back we go, the stranger the record becomes, almost as if time itself is playing favourites, preserving random fragments while erasing the rest. This is not just an accident, it is part of the design of the planet. Earth is not a museum. It does not keep archives. It does not care about memory. Everything we know about the ancient world comes from the narrowest slices of chance, from the moments when geology, biology, and luck all aligned long enough for something to enter the fossil record. And because of that, the story we have is not the complete story. It is not even close. Imagine a vast mansion stretching out in every direction with thousands of rooms, staircases, and chambers. Now imagine walking through that mansion at night with a single candle. A faint golden circle of light flickers on the walls around you, illuminating one room at a time while the others remain in total darkness. That is what studying Earth's history is like. Every new discovery opens the door to a new room, but the hallway behind it remains pitch black, stretching further than we can see. And before we wander any deeper into these dim corridors of time, feel free to pause for a moment. Tap the like button if you're enjoying this journey so far, and let me know in the comments where you're listening from and at what hour. As always with our stories, the images you see are simply companions to the narrative, helpful for mood but never required. Thank you truly for being here with us. Wherever you are in the world tonight or today, I wish you a peaceful, gentle moment as we step forward together. Scientists call it the problem of deep time, not because the time itself is deep, but because our vision is shallow. We are trying to reconstruct hundreds of millions of years from a handful of moments frozen in stone. And yet, every one of those moments matters because they hint at the existence of everything we cannot see. There is a principle in paleontology known as the senior lips effect. It states that the last fossil we find is almost never the last individual of its species. In other words, every extinction we think we understand is probably wrong by thousands or even millions of years. Fossils end abruptly, not because the species ended, but because the record ended. Nature did not stop. Only our evidence did. This principle applies not just to extinctions, but to origins, transitions, climates, landscapes, and entire worlds we know must have existed, but can no longer see. This is the heart of the paradox. The fossil record is not a story. It is a flicker of light, scattered and incomplete, and we spend our lives trying to turn it into a narrative. We are creatures wired for storytelling, trying to make meaning out of silence. We look at fragmented bones, imprints of leaves, chemical signatures in ancient rock, and we try to imagine the world they came from. But that world is not here anymore. Most of it has been erased, crushed beneath oceans, ground into dust by glaciers, buried under lava plains, or pulled down into the mantle where all traces melt away. And the erasure is not uniform. Some epochs glow brightly in the record, their fossils preserved in perfect detail, while others are nearly blank. Entire chapters are missing. The first 10 million years after the dinosaurs died, the rise of early primates, the moment when apes first stepped into the grasslands, the origins of our own genus. These are not small footnotes. They are foundational events in the story of life. They shape the world we live in now, and we can barely see them. If you look closely, patterns begin to emerge in the emptiness. The gaps are not random. They cluster around moments of change, around transitions, around upheavals. The more important the event, the fewer fossils we tend to find. It is almost poetic in a way, as if the universe is telling us that transformation is always hidden, always quiet, always lost in the noise. We see what came before. We see what came after. But the becoming, the changing, the moment when everything shifts, that part disappears. There is another layer to the paradox. The closer the timeline comes to us, the more detail we expect. After all, humans have lived on this planet through ice ages, migrations, bottlenecks, and climate swings. We imagine that our recent past should be visible, that the millions of people who lived during the Pleistocene must have left behind traces. And yet, when we look for them, we find almost nothing. A tooth here, a jaw fragment there, a few tools scattered across ancient riverbeds. Entire populations vanished without leaving a single artifact. If the ancient story of Earth is written in incomplete sentences, then the story of humanity is written in ellipses. We see the outlines of our origins, but not the details. We see the effects, but not the causes. We see footprints where a person once walked, but not the face of the person who made them. And so the story of human evolution becomes another room in the mansion, dimly lit, with doors leading into deeper darkness. This is why the gaps matter. They are not empty space. They are invitations. They ask us to imagine what might be hidden behind the silence. They ask us to consider that our picture of the past is not a finished painting, but a sketch drawn over smudged charcoal. They remind us that every certainty we hold is only a temporary truth, subject to revision the moment a new fossil is found in the dust. And so, when we begin to explore the erased worlds that came before us, we step not into a museum but into a labyrinth, a place where absence is as important as presence, where silence holds as much weight as evidence, and where time has erased more than it preserved. Our journey begins with the brightest of the dark rooms, a moment when the sky fell, when the earth was struck, and when the world ended. A moment we think we understand, but whose aftermath hides one of the greatest voids in the fossil record. Before we move forward, take a breath. Remember the paradox. Remember the candle in the mansion. And now, let us walk into the first doorway together. 66 million years ago, on a day that began like any other, the world ended. Not slowly, not gradually, not as a fading chapter in a long story, but in a single moment so violent that its scars can still be read in the rocks of every continent. If you could stand there and watch it happen, you would see nothing at first. A calm morning, warm air, forests thick with life, creatures grazing, hunting, calling to one another, a planet at the height of its own confidence, and then above them a point of light. It came from deep space, far beyond the orbit of Mars, far beyond the slow dance of the planets. A 6-mile-wide asteroid moving faster than a rifle shot, carrying more energy than every nuclear weapon humanity will ever build. In its final seconds, it tore through the atmosphere, superheating the air until the sky itself glowed white. Shadows vanished. The world brightened as if a second sun were rising. Then the light hit the coast of what is now the Yucatan Peninsula, and the world changed. We often talk about the asteroid as if it were the killer, but that is not quite true. The real destruction came after. In the moment of impact, trillions of tons of rock vaporized instantly. A crater nearly 100 miles wide and 12 miles deep opened like a wound in the crust. The shockwaves circled the planet within minutes. Forests fell, mountains shook, seas rose and collapsed again. But the true extinction did not come from the shockwave, or the fireball, or the tidal waves. It came from the rain. Molten droplets, vaporized rock heated to thousands of degrees, fell back through the atmosphere, igniting the sky. For hours the entire planet glowed red. Every forest on Earth caught fire at once. Animals thousands of miles away, untouched by the blast itself, suddenly found themselves in a world where the air was too hot to breathe. A global infrared pulse turned the surface of the planet into an oven. Those who survived the fire soon faced something worse. The fine particles launched into the stratosphere did not fall. They drifted, suspended above the clouds, forming a shroud that blocked out the sun. Not partly, not dimly, but completely. For months or years, Earth remained in darkness. Photosynthesis stopped. Plants died. Ecosystems collapsed from the bottom up. Herbivores starved first. Predators lasted longer, but not much. By the time light returned, 75% of all species on the planet were gone. Entire worlds disappeared. Not just the dinosaurs, but the forests they lived in, the insects that fed them, the small animals that shared their ecosystems. Even the great rivers and coastlines changed, reshaped by floods and ash. The world before the impact was not simply damaged, it was erased. And yet, something even more mysterious happened next. When we look into the fossil record, we can see the dinosaurs clearly. We can see their world, their bones, their footprints, their final moments. We can see the thin layer of iridium-rich clay marking the day the asteroid landed. We can see the ash, the soot, the burned pollen. But after that layer, something strange occurs. The world goes silent. For the first hundreds of thousands of years after the impact, the fossil record almost disappears. It should be a period of rebirth, of recovery, of rapid evolution. It should be a window into one of the most dramatic transitions in the history of life. But instead, it is a void, a blank page. We know small mammals survived. We know birds survived. We know crocodiles and turtles, and some fish endured the chaos. But for a long stretch after the event, we cannot see what they did, how they adapted, or how they evolved. The evidence is missing, not because nothing happened, but because everything happened in places and ways that left no trace. This is the most frustrating mystery of all. The moment right after the extinction should be the clearest. A fresh start. An empty world waiting to be filled. But instead it is the darkest chapter, a silence where a story should be. Part of the mystery lies in the violence itself. Ecosystems were disrupted, sediments shifted, lakes dried and refilled, coastlines transformed. Fossils form only under stable conditions, and stability was the one thing the post-impact world did not have. The survivors were few, scattered, and living on the edge. Their bodies rarely found the quiet burial conditions needed for preservation. But the silence may also reveal something deeper. The asteroid struck a world already under stress. Volcanic eruptions in the Deccan Traps had been flooding the atmosphere with carbon dioxide for hundreds of thousands of years. Some researchers believe the biosphere was already in decline. Others argue it was thriving, and the asteroid ended it abruptly. The truth is lost in the missing layers. We see hints on either side, but the transition itself is a void. There is another curiosity. Despite decades of debate, researchers still cannot agree on whether dinosaurs were declining before the impact. Some studies suggest falling diversity. Others point to sampling bias and gaps in preservation. The fossil record cannot tell us definitively. The last dinosaurs we see in the rocks may not be the last dinosaurs that lived. Their true final days are hidden beneath erosion, missing sediments, and the chaos of the impact. And so, we stand before one of the greatest ruptures in Earth's history, staring at the thin line of clay that marks the day the sky fell. Above the line is everything that came after: mammals, forests, oceans, climates, the seeds of our own existence. Below it is the vanished world of the dinosaurs. But the line itself, the moment of transition, remains shrouded in darkness. These missing years matter. They shape the future of life on Earth. They determined which species survived, which adapted, and which paths evolution took next. They influenced the rise of mammals, the return of forests, the patterns of climate, and the rebuilding of ecosystems. Everything that followed was born in this silence. And now, as we step forward, we enter a world struggling to rebuild itself from the ashes, a world where life must reinvent itself. But the road to recovery is far from clear. What comes next is not a triumphant rebirth, but a soft, flickering dawn. A dawn we can only see in fragments. When the ash finally settled and the fires died down, Earth entered one of the strangest periods in its long history. The sky brightened, the temperatures slowly climbed, and the world that emerged after the darkness bore almost no resemblance to the one that came before. It was a planet stripped bare, a global landscape of silence and opportunity, waiting for something new to take shape. This was the Paleocene, the first 10 million years after the extinction, a time when the world should have been filled with signs of recovery, with evidence of rapidly changing life and new evolutionary experiments. And yet, when we look into the rocks, this era appears dim and fragmented, as if most of what happened slipped past the eyes of time without leaving a trace. The Paleocene is often imagined as a quiet interlude, a slow rebuilding. But the truth is far more dramatic. Life did not simply return, it surged, it exploded, it reinvented itself in ways we still do not fully understand. And it did so at a speed that should have left a dense fossil record. Instead, it left gaps, vast ones. In the immediate aftermath of the impact, the animals that survived were those with the simplest requirements. Small mammals that could hide underground, birds that could eat seeds and insects, reptiles with slow metabolisms. Everything large, everything specialized, everything that needed an established ecosystem had vanished. The world belonged to the small, the adaptable, the invisible. But within a blink of geological time, that began to change. Studies of a few rare fossil sites show that mammals doubled in size within the first 100,000 years of the Paleocene. 100,000 years may sound long, but in evolutionary terms it is the span of a breath. Species that had spent millions of years living as tiny nocturnal scavengers suddenly found themselves in a world without giants, without predators, without the constant threat of being hunted. For the first time in their lineage, they had space. And they grew into it. Within 300,000 years, some mammals reached sizes 100 times greater than their ancestors. These were not giants by the standards of the later Cenozoic, but they were giants compared to the creatures that had survived the extinction. It was a planetary renaissance measured not in slow steps, but in leaps. And yet we see almost none of it. The evolutionary story of the Paleocene should be written across thousands of fossil beds. It should show the branching of lineages, the development of new forms, the reshaping of ecosystems, but instead the record is scattered, broken, incomplete. We see the before, we see the after, and in between there is only a thin scattering of bones, teeth, and hints. The reason is simple and frustrating. Fossils form best in stable environments, and the Paleocene offered almost no stability at all. The world was still reeling from the impact. Sea levels were shifting, climates oscillating, landscapes eroding and reforming. Rivers changed course, forests grew, died, and grew again. The sedimentary lakes and floodplains that usually preserve the history of life were rare and short-lived. Even when animals did die in ways that might have allowed preservation, their populations were small and dispersed. The survivors of the extinction had been pushed into ecological corners, living in isolated pockets, scattered refuges. Their bodies rarely found the quiet, uninterrupted burial conditions needed to become fossils. Instead, they decomposed, washed away, or were consumed by scavengers long before sediments could cover them. This absence is not emptiness. It is a sign of how turbulent the world was. The silence in the fossil record tells us not that little happened, but that everything happened too quickly, too unpredictably, and in the wrong places for fossils to form. What fragments we do have offer tantalizing glimpses of a world in flux. Fern prairies spread across continents burned by firestorms. Flowering plants, once overshadowed by conifers in the age of the dinosaurs, burst into dominance, filling open land with new colors and scents. Forests thick with broad leaves formed canopies whose shade created entirely new microhabitats below. Small mammals learned to climb, to glide, to hunt, to forage. Some became omnivores with crushing teeth. Others became timid browsers, feeding on young shoots and seeds. And yet, even these glimpses hide more than they reveal. Entire groups of mammals rose during the Paleocene, thrived for millions of years, and then vanished completely by the next epoch without leaving descendants. They appear in the record like ghostly experiments, evolutionary trials erased before they could shape the future. We know almost nothing about their behavior, their habitats, or the reasons for their disappearance. One such group, the multituberculates, had survived alongside the dinosaurs for over 100 million years. They flourished in the early Paleocene, diversifying into dozens of species. Then suddenly and inexplicably, they vanished. No decline recorded, no evidence of transition. They are present in one layer and absent in the next. A lineage older than most continents ended without a traceable cause. The Paleocene also holds the earliest branches of the primate family tree. Somewhere in this era, the first true primates emerged, small creatures with grasping hands, larger eyes, and more complex brains than their predecessors. These were the first steps toward the lineage that would one day produce humans. But these steps are almost invisible. The fossils are rare, fragmentary, and scattered. They hint at a beginning we cannot fully see. By the late Paleocene, forests stretched from pole to pole. The world grew warmer, more humid, more alive. But beneath this lush surface, pressures were building. Carbon dioxide levels were rising. Ocean chemistry was changing. Something vast was about to begin, something that would push the world into one of the most extreme climates it had ever known. The Paleocene is often treated as a footnote to the extinction event, a quiet chapter between disaster and recovery. But in truth, it is a blurred prologue to a far stranger story, a story of a world regrowing itself, of life experimenting wildly, of ecosystems rising from ashes in ways we can barely reconstruct. And hovering above it all is the strangest truth of all. The Paleocene is one of the most important eras for understanding how we came to be, and yet it is one of the blindest spots in the entire fossil record. A chapter that should be full of answers instead contains mostly questions. Because the calm of the Paleocene was only the illusion before a fever that would push Earth into a climate so extreme that even today, our models struggle to explain it. By the end of the Paleocene, the world had grown warm. Not unpleasantly warm, not dangerously warm, but lush and thriving, the kind of warmth that makes forests expand and rivers swell. Life seemed to be settling into a new rhythm, a steady calm after the violence of the extinction. But beneath that calm, pressures were building deep within Earth's systems, pressures we can still detect today in the chemical signatures locked inside ancient sediment. 56 million years ago, those pressures broke. In an episode now known as the Paleocene Eocene thermal maximum, or PETM, Earth entered a fever unlike anything in the age of mammals. Global temperatures rose between 5 and 8 degrees Celsius, and they did so with shocking speed. Not over millions of years, but over thousands, perhaps even centuries. It was a spike so abrupt that our modern climate models struggle to reproduce it. Something enormous happened, something powerful enough to tip the entire planet into a greenhouse it had not seen since the age of the dinosaurs. We know this much. Carbon flooded the atmosphere. It may have come from volcanic eruptions, from methane hydrates released in massive bursts from the ocean floor, from burning peatlands, or from some combination of these forces. Whatever the cause, the outcome was the same. The world changed faster than ecosystems could adapt. The first thing to shift was the air. Winters grew warm enough to erase seasonal cycles. Summers became tropical from pole to pole. Rainfall patterns transformed. Storms intensified. And the forests responded with explosive growth, spreading across continents in thick, tangled networks of vegetation. Then the oceans changed. They absorbed the excess carbon, turning more acidic. Deep sea creatures experienced widespread extinction. Coral-like communities collapsed. Temperature gradients shifted so dramatically that currents reorganized themselves, altering the movement of heat around the planet. But the most astonishing transformation occurred at the poles. For most of Earth's history, the poles anchored the climate with cold. Ice, snow, and frigid waters balanced the planet's heat. But during the PTM, those anchors disappeared. The Arctic became a warm sea. The Antarctic, which today is a frozen continent wrapped in storms, was covered in forests. Fossil evidence shows that trees resembling modern tropical species grew in what are now polar regions. In some places, crocodiles swam in waters that today lie beneath miles of ice. This world was not just warm, it was unrecognizable. And that is where the mystery begins. Even with high atmospheric carbon dioxide, even with supercharged greenhouse feedbacks, the temperatures at the poles during the Pertum remain difficult to explain. Modern models underestimate the warmth by a wide margin. Something in Earth's climate system behaved differently back then, something we do not fully understand. There may have been feedbacks now lost, cloud patterns we cannot reproduce, ocean circulation modes that no longer exist. The exact mechanism remains one of the most stubborn puzzles in paleoclimatology. If there were ever a period that should be richly preserved in the fossil record, it is this one. Warm, wet conditions support dense life. Vast forests were home to primates, birds, early hoofed mammals, and predators unlike anything alive today. Rivers and floodplains should have buried carcasses beneath layers of sediment. Coastal swamps should have trapped plants and insects in soft, oxygen-poor mud. And yet, the fossil record of the PETM is strangely thin. There are windows into this world, but they are scattered across the globe, tiny preserves of ancient time. A fossil-rich basin in Wyoming, a handful of marine sites in Europe, a few stretches of exposed sediments in Asia. Each one offers a glimpse, but never the whole. They are like shards of a broken mirror. We see reflections of forests, of primates, of new mammal lineages emerging and shrinking, of species shrinking in size to cope with the heat. But the mirror is incomplete, and most of its pieces have vanished. A major reason lies in the very thing that made the PTM so lush. Tropical forests, especially warm, wet forests, are some of the worst environments on Earth for preserving fossils. The heat accelerates decay. The constant churning of plant roots disturbs sediments. The acidic soils dissolve bone. Even when animals die in places that might preserve their remains, scavengers and microbes reduce them to fragments within days. The result is a world we know existed, but can barely reconstruct. we know that primates diversified rapidly during the PETM. In fact, the earliest ancestors of modern monkeys, apes, and humans likely emerged during this time, adapting to forests filled with fruits, flowers, and opportunities for climbing. But the fossils that should document their rise are missing. What we have is only enough to tell us that something happened, not how it happened. We know that hoofed mammals evolved new forms, some resembling tiny horses, others resembling tapirs or deer. But the transitions between these forms are mostly absent. They appear in the record already distinct, as if the process of their evolution occurred in a place where fossils rarely form. We know that predators changed as well. Entire families of carnivorous mammals thrived for millions of years before vanishing without descendants. One moment they are abundant, the next they no longer exist. Their disappearance is as sudden in the record as their appearance. But perhaps the strangest mystery is that the PETM was not the peak of Earth's greenhouse conditions. It was only the beginning. The Eocene, the epoch that followed, carried the warmth forward for more than 20 million years. For 2 entire geological eras, Earth was a hothouse world, a planet without ice, a world glowing under a heavy sky. And still, much of its story is missing. The PETM stands as a doorway. On one side lies the chaos of the extinction. On the other lies the warmest age of the Cenozoic. But the doorway itself remains narrow, crowded with unanswered questions. What triggered the sudden temperature spike? What feedbacks amplified it? Why did the poles become so warm that crocodiles could thrive in places now frozen solid? Why do our climate models fail to capture its extremes? If this was the dawn of primates, of new mammals, of whole lineages, why does the fossil record remain so faint? We know something enormous happened, but the details are lost in the very forests that flourished because of it. Now, as the Paleocene fades and the Eocene begins, the world becomes stranger still. It is time to step into a landscape where nothing looks familiar, where life blossoms in forms that seem almost alien, and where the story becomes even harder to follow. When the Eocene dawned, it did not arrive quietly. It rose out of the fading heat of the PETM like a new sun, bright, humid, and impossibly warm. For the next 22 million years, Earth existed in a state so foreign to the modern mind that it feels almost imaginary. A greenhouse world wrapped in lush forests, with no ice anywhere, not in the mountains, not at the poles, not even in the shaded corners of the far north. Imagine standing in what is now Alaska. Instead of tundra and silence, you would find yourself surrounded by towering palms and broadleaf trees, their leaves shifting in warm breezes. Rivers wound through dense vegetation. Frogs croaked from the water's edge. Insects buzzed in thick clouds. And on the banks, basking lazily, were crocodiles. Creatures typically associated with tropical rivers thrived at the top of the world. This was not just a warm planet, it was a planet without winter. The temperature difference between the equator and the poles was smaller than it is today by an order of magnitude. Seasonal variation was muted. Tropical conditions extended far into what we now think of as temperate zones. Rainfall patterns were radically different, and the ocean, freed from the anchoring cold of polar ice, circulated heat far more efficiently, smoothing temperature gradients across entire hemispheres. But the deeper mystery is not how warm the Eocene was. It is why. Even with elevated carbon dioxide levels, even with greenhouse feedbacks from the PETM still echoing across the climate system, the warmth of the poles during the early Eocene defies our best models. Something is missing from our understanding. Some mechanism, some atmospheric pattern, some oceanic circulation, some cloud behavior that allowed the poles to remain as warm as subtropical coastlines. We can say what the world looked like, but we cannot yet say how it worked. As the climate stretched into this long, stable warmth, life responded with an explosion of diversity. Mammals, in particular, entered a phase of evolutionary experimentation that reshaped the entire biosphere. In the absence of dinosaurs, they evolved into forms that would seem almost alien now. Early horses no larger than modern house cats darted between trees, their toes still splayed for the soft forest floors. Whales, still tied to the land, padded along coastal plains on legs that had not yet transformed into flippers. Bats appeared suddenly in the fossil record, already capable of flight, leaving their flightless ancestors entirely absent. Elephants, rhinos, and tapirs began their long, branching histories from ancestors that scarcely resembled the giants of today. And there were creatures without any modern descendants at all. Entire families of mammals thrived for millions of years before disappearing completely, leaving behind only fragments of jawbones, isolated teeth, or handfuls of skeletons in rare fossil beds. Among these vanished experimentations were the creodonts, a lineage of carnivorous mammals unrelated to modern predators. Some were the size of wolves, others the size of bears, with skulls elongated in unfamiliar ways and limb proportions unlike any carnivore alive today. For tens of millions of years they dominated the continents. Then they vanished, replaced gradually by the ancestors of today's cats, dogs, and hyenas. Their rise and fall is written in only a few scattered fossils. The Brontotheres were stranger still. Massive herbivores with deeply forked Y-shaped horns. They towered over early forests, some reaching the size of modern rhinos. They spread across North America and Asia, thriving in the Middle Eocene before disappearing entirely. Their extinction leaves no clear explanation. Climate change, most likely. Competition possibly. But the fossil record around their decline is too fragmented to show the steps. Even the early primates, the ancestors of all monkeys, apes, and eventually humans, emerged and diversified during this epoch. They evolved larger brains, forward-facing eyes, and grasping hands. But again, their story is incomplete. We see their presence. We see their adaptations. But the transitions between their earliest and later forms remain largely invisible. Why is the fossil record of such a richly populated world so thin? The answer lies in the forests themselves. The Eocene was dominated by warm, wet forests that stretched across continents. These environments are the worst possible places for fossils to form. The constant humidity accelerates decay. The dense root systems churn the soil. Acidic leaf litter dissolves bone. Decomposers work quickly, leaving almost nothing behind. Even if an animal dies in a floodplain, the sediments may be disturbed before they can preserve anything. The result is a paradox. The Eocene may have been one of the most biologically vibrant periods in Earth's history, yet it is one of the most poorly represented in the geological record. We can infer the presence of ecosystems that left almost no physical trace. But the Eocene was not static. Beneath the steady warmth, deep tectonic forces were reshaping the world. India continued its collision with Asia, raising the Himalayas higher each million years. Mountain building altered winds, monsoons, and rainfall. The Atlantic widened. Ocean gateways opened and closed. Currents shifted. These tectonic rearrangements set the stage for the next great transformation in Earth's climate. A shift so sudden and severe that it ended the Eocene and rewrote the climate of the planet. But before the crash came another mystery. During the long heat of the Eocene, early anthropoid primates underwent crucial evolutionary changes. They began to diverge from their more primitive cousins. They developed traits that would eventually lead to monkeys, apes, and the lineage that leads to us. Yet almost every species bridging these transitions is missing. Their fossils may have formed in forests that left no trace, or in sediments later destroyed by mountain building. In this way, the Eocene becomes not just a world that defies our climate models, but a world that defies our evolutionary understanding. It is a chapter where life flourished beyond our visibility, where creatures took forms we can glimpse only faintly, and where entire evolutionary lineages began, shifted, and disappeared without a clear record. The world that rose after the dinosaurs was strange, but the world that followed it, the warm Eocene, was stranger still, and as the epoch drifted toward its end, the planet braced for a climatic event that would shatter the equilibrium of millions of years. The warmth would break, the forests would retreat, and a new kind of world would emerge, one that looked more familiar to us, but less forgiving to the creatures that had evolved in heat. The warmth of the Eocene did not end with a slow decline. It ended with a break, a fracture, a shift so abrupt that entire ecosystems collapsed before they could adapt. Around 34 million years ago, the planet crossed a threshold, and the world that had existed for tens of millions of years simply vanished. This was the beginning of the Oligocene, the first true winter of the Cenozoic, a cooling so profound that Antarctica transformed from a forested continent into a frozen desert in what was, geologically speaking, the blink of an eye. The cause of this sudden chill lies in plate tectonics, in the slow rearrangement of continents moving millimetre by millimetre until they finally crossed invisible tipping points. As South America drifted away from Antarctica, and as Australia continued its migration northward, a new ocean gateway opened around the southernmost part of the world. This allowed a powerful new current to form the Antarctic Circumpolar Current, a ring of cold water that isolated the continent from the warm oceans to the north. Once that current began, Antarctica froze. Ice spread across the land, thickening each year. Snowfall compacted into glaciers. Glaciers grew into ice sheets, and as Antarctica turned white, sunlight reflected back into space, cooling the entire planet even further. What began as a regional shift cascaded into a global transformation, but here again, the fossil record plays a trick on us. We should see a gradual transition from lush forests to cooler woodlands, then to open habitats, then to the first grasslands. We should see mammal species adapting, shrinking or growing, altering their diet, changing their behaviours. We should see the slow rise of lineages better suited to colder, drier climates. Instead, we see only fragments. In the rock layers around the transition, one moment the world is filled with Eocene life, and in the next, it is gone. Entire families of mammals that had thrived during the warm epoch disappear suddenly, replaced by creatures better adapted to the new climate. Where were the intermediates? Where were the transitional environments? Where were the species caught halfway between the old world and the new? The answer once again lies in preservation. The upheaval that accompanied the onset of the Oligocene did more than cool the planet. It disrupted rivers, drained wetlands, erased floodplains, and altered coastlines. The very environments that normally preserve fossils were being destroyed and rebuilt. Sediments that could have recorded the change were washed away or never deposited at all. And so the transition appears sharper than it likely was, not because nature made an instant change, but because the record of the change was lost. The animals most affected by this upheaval were those that depended on the dense, warm forests of the Eocene. Many primate lineages vanished from northern continents. Hoofed mammals adapted to browsing on soft leaves found themselves struggling as vegetation became sparser and tougher. Carnivores that hunted in dense undergrowth now confronted open, colder landscapes that favoured very different hunting strategies. But while many species declined, others rose. With the cooling came the first great expansion of grasslands. Grasses had existed for millions of years, but only in small pockets. Now, as forests retreated, grasses found room to spread, creating the first true open plains. These new habitats reshaped mammal evolution. Animals evolved longer limbs for running, larger eyes for spotting predators at distance, and more complex teeth for grinding abrasive grasses. The earliest forms of rhinos and horses began their long story here, in the sparse but expanding plains of the Oligocene. Their ancestors, built for life in forests, gradually vanished, while newer species better suited to open terrain took their place. Under the surface of this ecological shift, deeper processes were at work. Mountain ranges continued to rise, the Himalayas still climbing as India pressed into Asia, the Alps forming as Africa pushed northward, the Rockies being reshaped by tectonic forces. These rising mountains altered weather patterns, blocking moisture, creating rain shadows, and further drying continental interiors. With each geological adjustment, ecosystems reshuffled. Species migrated or went extinct. Rivers carved new paths through uplifted terrain. Entire regions shifted from wet to dry, from forest to steppe. Yet the fossil record from this time is frustratingly incomplete. The Oligocene should show the earliest apes branching from their primate relatives. It should show the origins of many modern mammal families. It should reveal how early carnivores diversified into the forms we recognize today. But instead, we are left with isolated fossil sites that give us only snapshots of this crucial period. In some regions, primates vanish entirely from the record for millions of years. In others, hoofed mammals appear as if fully formed, with little evidence of the intermediate steps that must have occurred. Even the spread of grasslands, such a monumental ecological shift, leaves only scattered sedimentary clues. And then there is the biggest mystery of all. Somewhere in the Oligocene, the ancestors of the great apes must have first emerged. This was the era when certain primates developed the traits that would later lead to monkeys, gibbons, orangutans, gorillas, chimpanzees, and eventually humans. Yet fossils documenting this transition are almost non-existent. We know these lineages must have begun diverging. We know the genetics demand it. But the bones that should tell the story are missing. They may have evolved in forested regions that left no fossils, or in sediments later destroyed by erosion, uplift, or volcanic activity. They may lie buried under rock we have yet to expose. Or they may have formed in environments where fossilization simply never occurred. The Oligocene is a hinge in the story of life on Earth, a point where the world pivoted from the ancient heat of the Eocene toward the drier, cooler, more seasonal climates that would define the next 40 million years. But as with every hinge, the movement happens fast, and the evidence of the movement is subtle. What we see now is the world after the hinge has swung, colder, harder, more open. A world on the verge of the great grassland expansions that will reshape evolution. A world where ancient primates must adapt or disappear, and as the Oligocene draws to a close, a new epoch rises. One that should reveal the missing chapters of our own story. One that should show how the ancestors of humans took shape. But instead, the next era plunges us into an even deeper mystery. A long stretch of time where the world should be full of clues about our origins, yet somehow, almost everything is missing. The Miocene begins around 23 million years ago, and on paper, it should be one of the clearest, richest, and most revealing periods in the entire history of life. This is the epoch when modern ecosystems began to take shape, when grasslands expanded across continents, when great mountain ranges reached their full height, and when the ancestors of countless living species spread into new environments. But for the story of our own lineage, the Miocene is not a window, it is a wall. Somewhere in this 20 million year stretch, the great apes emerged. Their branches diverged. Their ancestors spread across Africa, Europe, and Asia. They grew larger brains, new body plans, stronger social structures. They adapted to shifting climates and changing landscapes. They became, in essence, the creatures that would eventually produce humans. And yet, for all the importance of this era, the fossil record refuses to tell us the story. The Miocene should show the step-by-step transformation from early primates into the first apes. It should show the origins of gibbons, orangutans, gorillas, chimpanzees, and the early hints of the lineage that would lead to hominins. It should be filled with transitional species, branching experiments, evolutionary trials. Instead, what we have are fragments: a jawbone here, a partial skull there, a handful of teeth scattered across time and continents. This is the age when the largest number of ape species in history existed, yet we have fewer fossils from this entire epoch than from some single sites in the age of dinosaurs. Why is the record so thin? To understand this, we have to understand the world the apes lived in. As the Miocene unfolded, Earth's climate grew cooler and drier. The great warm forests of the Eocene and early Oligocene continued to retreat. Grasslands expanded across Africa and Eurasia. River systems changed as mountains rose. Rainfall patterns shifted as tectonic forces reshaped continents. The world was no longer a greenhouse wrapped in a uniform canopy of trees. It was becoming patchy. Forests, open woodlands, savannas, and deserts forming a mosaic across the continents. This mosaic created opportunities. Species adapted to different pockets of habitat. Some apes thrived in dense forests, feeding on fruits and climbing high into the canopy. Others moved into more open woodlands, walking across branches and strengthening their limbs. Still others experimented with more terrestrial behavior, navigating the spaces between trees. But mosaic environments are terrible for fossil preservation. The places where early apes lived were dynamic and unstable. Forest floors were acidic. Open woodlands experienced seasonal floods and droughts that destroyed remains before they could be buried. Many of the regions where apes evolved were being uplifted by tectonic forces, tilting and fracturing the sediments that might have preserved their bones. And beyond all of that, there is a harsh truth. Most animals never fossilize. Fossilization requires precise conditions: rapid burial, gentle sediments, the right chemical environment, protection from scavengers, and millions of years of undisturbed rock. Most Miocene apes lived too far from lakes and floodplains, too deep in forests, or too high in terrain that would later erode away. The result is a fossil record full of ghosts. We know they were there because genetics demands it. DNA comparisons between living apes show that the lineages had already split deep within the Miocene. The ancestors of gibbons diverged first, then orangutans, then gorillas. Then the split between chimpanzees and humans. These splits are measured in genetic clocks, not bones. The bones, for the most part, are gone. But the fragments we do have hint at a world full of complexity. In East Africa, fossils show large-bodied apes with strong jaws and heavy limbs, suggesting slow-moving creatures similar to early gorillas. In Europe, fossils reveal long-limbed apes that may have been among the first to walk upright on branches, using their arms for balance. In Asia, we see early relatives of orangutans already distinct in their features. Each fossil is a clue, but none of them connect. They are like isolated sentences torn from a book with all the pages missing. The greatest frustration comes from the timeline of human origins. Genetic evidence suggests that the ancestors of humans and chimpanzees diverged somewhere between 6 and 8 million years ago, near the end of the Miocene. That divergence should be recorded in the fossil record. It should be visible in a sequence of transitional species, showing the slow shift toward bipedal anatomy, toward new diets, toward changes in the skull, spine, pelvis, and limbs. But almost nothing from this critical window remains. Instead, the record jumps from scattered Miocene apes to the earliest known hominins in the Pliocene, millions of years later. It is as if the middle chapters of our story were written down and then thrown into the wind. And it is not just our lineage. Other great ape lineages also vanish and reappear abruptly in the record. Gorillas have almost no fossil history. Chimpanzees have almost no fossil history. Even orangutans, the most distinct of the great apes, have deep ancestral gaps. All of this raises a haunting question. Where did the apes go? Not literally, but in terms of record. Where are the fossils they must have lived, thrived, reproduced, and died by the millions? They must have filled forests and woodlands across continents. They must have left bones. But time erased them. The Miocene is not an empty epoch. It is an overwritten one. Its sediments have been uplifted, eroded, drowned, and transformed. Its fossils have been dissolved in acidic soil, crushed by tectonic forces, or buried in places we have not yet searched. And the world they inhabited was one in motion. Grasslands expanding, forests shrinking, climates oscillating, species migrating across continents, evolution running in dozens of directions at once. The Miocene should have been the chapter that explained the origins of the apes. Instead, it has become one of the greatest cold cases in science. But as the Miocene ends and the Pliocene begins, something remarkable happens. The world settles into a new rhythm, and the first faint outlines of our own lineage appear. Not clearly, not fully, but enough to show that the long-hidden story is finally emerging from the shadows. When the Miocene finally gave way to the Pliocene, around 5 million years ago, Earth had already reshaped itself into a world that looked far more like the one we know today. The climate cooled further. Grasslands spread across Africa and Eurasia. The forests retreated into narrower, fragmented bands. The seas rose and fell with the swelling of glaciers. The continents rested roughly where they are now. This should have been the moment when the story of our lineage came into sharp focus. The great apes had already split into their separate branches. The ancestors of humans and chimpanzees had diverged. The first hominins should be visible, scattered across the landscape, leaving behind a trail of bones marking the earlier steps toward upright walking, tool use, and the complex minds that would one day shape the planet. Instead, the Pliocene greets us with a quiet, frustrating truth. Nearly everything is missing. We know that early hominins existed. We know they were experimenting with forms of bipedalism, with new diets, and with new ecological niches. We know they must have spread across Africa in small, scattered populations. But the fossil record that should document their journey is astonishingly sparse. In fact, when we list all of the major hominin fossils from the entire Pliocene, the total quantity could fit comfortably inside a single room. And yet the Pliocene is where some of the most iconic discoveries of human evolution reside. The famous Australopithecus afarensis specimen known as Lucy lived during this epoch. So did several other early hominins representing experiments in posture, locomotion, and feeding strategies. But these fossils, remarkable as they are, appear not as a continuous sequence, but as lonely islands in a vast ocean of missing time. Lucy, for example, represents a species understood better than most early hominins. But even with her, the picture is far from complete. We do not know exactly how her species arose. We cannot trace every trait to a specific ancestor. We do not know how many other hominins lived alongside her, or how many lineages rose and fell without leaving any trace. The Pliocene is a paradox. It contains the first clear evidence of our lineage, yet it hides almost everything about how that lineage developed. Part of the reason lies in the landscapes these early hominins inhabited. By the Pliocene, much of Africa was a patchwork of habitats: woodlands, grasslands, rivers, and seasonal wetlands. Early hominins likely moved between these environments, seeking food, water, and shelter. They may have lived in small groups, migrating according to seasonal rains. Such shifting landscapes are notoriously poor at preserving fossils. Bones left in the open are exposed to scavengers, weather, and decay long before burial can occur. Floods, droughts, and shifting sediments erase what little evidence might have formed. Another reason lies in population size. Early hominins were never abundant. They were not spread across continents like modern humans. They existed in small, isolated pockets, separated by geography and climate. Small populations mean fewer bodies left behind, fewer chances for fossilization, fewer snapshots of their existence. The result is a record full of beginnings, but lacking the middle. We see upright walking beginning to take shape. The pelvis, spine, and femur in some Pliocene fossils show clear adaptations for spending more time on two legs. But we do not see the generations that bridge the gap between knuckle-walking ancestors and fully upright descendants. We see changes in tooth structure, suggesting a diet that included more grasses, roots, and tough plant matter. But we do not see the gradual shifts in feeding behavior that led to these adaptations. We see the first hints of social complexity in the footprints at Laetoli, where individuals walked across fresh volcanic ash roughly 3.6 million years ago, leaving behind tracks that show size differences and coordinated movement. But we do not know who they were, how large their group was, or what they were doing. The footprints are a moment trapped in time, with no before and no after. And perhaps the most fascinating mystery of the Pliocene concerns the number of hominin species that existed. Based on genetic evidence and the branching patterns of later fossils, scientists believe there must have been many more hominin lineages than the ones we have found. Some may have lasted hundreds of thousands of years before disappearing. Others may have diverged from known species only to vanish without descendants. These are the ghost lineages of the Pliocene, evolutionary paths that left no bones but must have existed. This makes the Pliocene one of the most critical yet incomplete chapters of human evolution. It is the point at which our story begins to separate from the stories of every other ape. It is the period when our ancestors took forms that are recognizable as early humans. And yet, it is a chapter full of missing paragraphs, torn pages, and entire chapters that have drifted away. But the Pliocene was not only about hominins, it was also a time of sweeping global change. Sea levels rose and fell repeatedly as Earth's temperature fluctuated. Glaciers expanded and retreated in the northern hemisphere. Ocean currents shifted. Species migrated across continents through land bridges that no longer exist. Grasslands continued to expand, reshaping the distribution of animals across Africa and Eurasia. These changes set the stage for the next epoch, the Pleistocene, where the world would swing between glacial and interglacial cycles. A world where climate would become unstable, where habitats would shift back and forth with dizzying speed, and where early humans would be forced to adapt or disappear. And yet, despite the dramatic environmental changes of the Pliocene, our ancestors endured. They adapted to the patchwork landscapes of Africa. They learned to walk upright in open terrain. They developed diets flexible enough to survive in changing environments. They formed social structures that helped them navigate uncertainty. The Pliocene is the whisper before the storm. It is the faint outline of the story that is about to unfold. But as soon as the first shadows of the Pleistocene stretch across the horizon, the world begins to change in ways that would challenge every creature alive. What follows is the age of ice, the crucible in which human evolution would finally take shape, and the era that hides its own labyrinth of missing history. When the Pliocene dimmed and the Pleistocene rose around 2.6 million years ago, Earth entered one of the most dramatic and unstable chapters in its history. Temperatures began to swing in vast cycles. Ice sheets advanced and retreated across continents. Sea levels rose and fell by more than 100 meters. Entire ecosystems shifted hundreds of miles north and south in response to the marching glaciers. The world became a pendulum, swinging between cold and warmth, between abundance and scarcity. And in this shifting landscape, early humans took their final shape. This should be the moment when our story comes into full view, when the fossil record becomes dense, when the world of the Pleistocene leaves clear traces in sediment, ice, and bone. After all, this epoch is recent. It is close. It is well within the time frame in which fossils should be plentiful. Instead, the Pleistocene presents us with one of the deepest mysteries of all. For reasons still debated, the fossil record of our closest relatives is astonishingly thin. We find Neanderthal bones, but not as many as we should. We find fragments of Denisovans, only a finger bone and a few teeth. We find hints of other hominins scattered across Africa and Asia, but never enough to follow a lineage clearly from beginning to end. The Pleistocene, in its richness and proximity to us, should be filled with answers. Instead, it is filled with shadows. Part of the mystery lies in the nature of the glacial cycles. When ice sheets advanced, they bulldozed everything in their path: forests, soils, fossils, and entire landscapes. When the ice retreated, torrents of meltwater washed away sediments that might have preserved remains. Vast areas of northern Europe, Asia, and North America were scraped down to bedrock over and over again by the grinding force of glaciers. Any fossils that may have existed there are simply gone. But the greater mystery lies not in what was destroyed, but in what is now hidden beneath the sea. During the peak of the ice ages, sea levels dropped by over 100 meters. This exposed enormous areas of land that today are underwater. The coastlines of every continent stretched far beyond their current boundaries. Entire regions the size of nations connected landmasses that are now separated by ocean. These lost lands include Beringia, the broad region that once connected Siberia to Alaska. It includes Sunderland, the landmass that joined Southeast Asia to Indonesia. It includes the Persian Gulf Basin, which may once have been a vast, fertile plain. It includes the shallow continental shelves around Africa, Australia, and the Americas. These were not marginal areas. They were some of the most hospitable environments on Earth. Rivers flowed across them. Forests and grasslands covered them. Human and animal populations likely thrived there. But as the ice melted and sea levels rose, these lands were swallowed by the ocean. Any traces of the people and animals who lived there now lie beneath tens of meters of water and sediment. This means that much of the story of early humans, perhaps most of it, took place in places that are now inaccessible. We search for fossils in caves, river valleys, and ancient lake beds. But the true centers of ancient human life may lie beneath the waves, locked away where we cannot yet reach them. This helps explain a long-standing puzzle. Why is there such a disconnect between the genetic diversity of ancient human populations and the fossil record that is supposed to represent them? Why do DNA studies suggest that multiple hominin species existed side by side, while fossils suggest only a handful? Why do stone tools appear far earlier and in far greater abundance than the bodies of the people who made them? The answer may be simple. The story happened somewhere else. During glacial maximums, coastlines extended far into what is now the ocean. Early humans could have lived along rivers that no longer exist, hunted on plains now underwater, travelled migration routes we can only guess at. When the ice melted, the ocean rose and covered those worlds, erasing nearly all evidence. A similar mystery surrounds the megafauna of the Pleistocene: mammoths, giant sloths, saber-toothed cats, woolly rhinoceroses, and dozens of other large animals thrived for hundreds of thousands of years. Yet their fossil record is uneven. Some regions preserve them in abundance, while others show only isolated remains. And when these animals suddenly disappeared around the world at the end of the Pleistocene, the record of their decline is thin and scattered. Were they hunted to extinction? Were they victims of rapid climate change? Were they undone by a combination of both? The truth hides in sediments we have not yet recovered. But the Pleistocene is not only a story of missing fossils, it is also a story of transformation. This is the age when humans learned to control fire, when they expanded their range across continents, when they adapted to deserts, forests, coasts, and plains. It is the age when symbolic behavior began, when early art emerged, when tools became more sophisticated, when language may have begun its ascent. And yet, for all this cultural richness, the physical record remains faint. We have footprints in volcanic ash. We have fragments of shelters built by ancient hands. We have tools carved from stone that endured long after the bones of their makers vanished. But the people who made them remain elusive. Their bodies decomposed in soils too acidic for preservation, or were washed away by floodwaters during interglacial transitions. The Pleistocene offers glimpses of our story, but holds back the narrative thread that should connect them. In this way, the Age of Ice is both familiar and alien. It shaped the world we know, yet its full history lies beneath ice sheets that melted, beneath oceans that rose, beneath layers of sediment that hide the truth. But as the Pleistocene drew to a close around 11,700 years ago, a new world emerged. The ice retreated. The seas rose to their current levels. The planet warmed. And humans stepped fully into the landscapes that would shape their future. The Holocene began. Civilizations would soon rise. But with their arrival came a profound realization. For all the clarity of recent history, the deep story remained broken, and the reasons for these breaks are woven into the planet itself. When the last ice retreated and the Pleistocene gave way to the Holocene, the world felt newly made. Rivers carved fresh paths through thawed valleys. Forests crept into regions where glaciers had dominated for tens of thousands of years. Coastlines settled into the shapes we now recognize on our maps. Humanity, at last, entered an era where its story could be written in more permanent ways. And yet, even as we stepped into recorded history, the deeper past remained fractured. The gaps, the silences, the missing chapters that haunted every previous epoch did not disappear simply because humans learned to build cities or carve symbols into stone. The forces that erased the past for millions of years did not stop working. They never stop. Earth is not a library. It is an engine of change. To understand why so much of the planet's history is missing, we must recognize that erasure is not an accident. It is the default state of the world. Every fossil we have exists only because it escaped erasure for a moment, because it slipped through the cracks of an unrelenting process. The vast majority of life leaves no trace at all. The creatures, forests, and worlds we imagine when we think of deep time are built from a tiny fraction of what once existed. Consider tectonics. Continents drift, collide, split apart, and reform. Entire mountain ranges are lifted toward the sky, only to be worn down to dust again. The floors of ancient seas are pushed upward into plateaus. The sediments that might have preserved 1,000 species are folded, crushed, melted, or subducted back into the mantle. The story written in those layers is gone, recycled into new rock. Consider erosion. Wind strips the surface. Rain carves channels. Rivers move sediments from one place to another, burying remains in one era and uncovering them in another. Glaciers grind landscapes into fine powder. Deserts scour bones until nothing remains. Even a stable environment lasts only temporarily before the next storm, flood, or drought reworks the land. Consider the sea. More than 2/3 of the continents once lay beneath shallower waters during ancient epochs. When sea levels fall, those coastlines rise into the air, exposing ancient sediment. When sea levels rise again, as they did repeatedly during the Pleistocene and into the Holocene, those same coastlines vanish beneath the waves. Whatever lived there, whatever built shelters or tools, whatever formed communities on ancient shores, is now sealed under layers of mud and sand on the ocean floor. If early humans or their ancestors built anything along the coasts of Africa, Asia, or the Americas during the Pleistocene or before, the ocean has claimed it. If entire cultures flourished on the exposed plains of Sunderland or the fertile lands of the Persian Gulf Basin, we may never know. Their evidence lies in places we have barely begun to explore. Even the parts of Earth that appear stable can betray us. Tropical forests destroy fossils through moisture and acidity. Mountain valleys hide sediment under layers of rockfall. Caves collapse. Floodplains shift. Volcanic eruptions bury entire landscapes beneath ash, preserving some remains while obliterating others. All of this means that the record we do have is not a complete history. It is a puzzle with pieces missing. Some pieces were never made. Others were destroyed. Others are buried too deeply to reach. And some may lie in regions we cannot yet explore, on continental shelves, underwater plateaus, or beneath ice several kilometers thick. But perhaps the deepest truth is this: the gaps in the record are not just failures of preservation. They are reflections of the way life itself evolves. Transformation rarely happens in places where fossils form. The great shifts in evolution occur in small populations, in isolated environments, in regions where sediments do not accumulate. The beginnings of new species, including our own, often occur in the shadows of the world in rainforests, cliffsides, coastal plains, mountain ridges, or floodplains that come and go with the seasons. By the time these species become abundant enough to leave fossils, the critical steps that shape them have already passed into invisibility. This is why we see the dinosaurs vividly, yet struggle to trace the origins of apes. This is why we can reconstruct ancient seas in extraordinary detail, yet cannot follow the emergence of human consciousness step by step. This is why the transitions that matter most, the rise of primates, the divergence of hominins, the beginnings of culture, are lost in the blur. And so, when we look back on Earth's history, we must accept that we are not reading a complete narrative. We are reading a collection of preserved moments scattered across time, connected by inference and imagination. We fill in the blanks because we must, because our minds cannot tolerate a story without meaning. But the blanks remain. This does not make the story weaker. It makes it human. We are creatures drawn to the unknown, compelled to explore the edges of knowledge, to illuminate the dark rooms of the mansion we inhabit. We gather fragments, dust them off, and try to understand how they fit. Each fossil is not just evidence, but an invitation, a reminder that the world is larger, older, and stranger than we can fully grasp. In the quiet of night, when we think of the deep past, we are not simply remembering what once was. We are listening for echoes in a house built by time, where most of the doors remain closed and most of the halls remain unlit. The story of Earth is not a story of certainty. It is a story of searching, a story of glimpses, a story of vanished worlds that shaped our own. And before we take these final steps toward the close of our journey, feel free to support this channel if you've enjoyed traveling through these forgotten ages with us. A like, a share, or even subscribing helps this little corner of the internet stay alive, so we can keep exploring these hidden chapters together. And as we close this journey, standing here in the warmth of the Holocene, surrounded by the comforts of a stable climate and the weight of our recorded history, we must remember that the past beneath us is still shifting. That somewhere below the continents, somewhere beneath the oceans, somewhere in the layers we have yet to uncover, more chapters wait, pages still sealed, worlds still hidden, and someday, when the light reaches further into the darkness, when new fossils emerge, when new stories rise from the stone, we may finally understand the parts of our history that time tried to erase. Until then, the mystery remains.